What if I told you that right now, at this very moment, something is hurtling through our solar system that makes scientists question everything they thought they knew about the universe? And I'm not talking about the comet you're thinking of. For years, we've been obsessed with Comet 2I Borisov and the bizarre interstellar visitor Oumuamua. We thought we'd seen strange. We thought 2019's Comet Atlas officially designated C 2019. Y4 was pushing the boundaries of weird when it dramatically disintegrated before our eyes. But here's what will absolutely shatter your understanding of our cosmic neighborhood. There's something out there right now that's rewriting the rules of what a comet can even be. I'm talking about an object so bizarre, so fundamentally different from anything we've cataloged in 4 centuries of astronomical observation, that when the team at the Asteroid Terrestrial Impact Last Alert System discovered it, they had to create entirely new categories just to describe what they were seeing. This isn't just another icy rock from the Oort cloud. This is something that challenges the very definition of comet. And the most mind-bending part? The reason 2I Atlas, yes, there's another Atlas, is no longer the strangest comet in our solar system, has nothing to do with it becoming normal. It's because we found something even more impossible. Before I reveal what that is, I need you to understand something crucial. What you're about to learn isn't just astronomy trivia. This discovery has implications for how we search for life in the universe, how we understand the formation of solar systems, and yes, how we assess potential threats to Earth itself. But first, if you're ready to have your mind completely blown about what's really happening in the darkness between planets, smash that like button right now. And hit subscribe, because we're going on a 3-hour journey into the most bizarre celestial mystery of our time. Also, drop a comment telling me where in the world you're watching from and what time it is for you right now. I want to know how many of you are staying up late for this cosmic revelation. Are you in Mumbai watching at midnight? Sydney at dawn? New York during your lunch break? Let me know. To understand why what we've discovered is so utterly bizarre, we need to establish what normal actually looks like in the world of comets. And trust me, even normal comets are spectacular enough. Picture this. It's 1705, and Edmund Halley, a guy with the famous comet, is sitting at his desk doing something revolutionary. He's comparing historical records of comet sightings, and he notices something extraordinary. The comets seen in 1531, 1607, and 1682 weren't different comets at all. They were the same object, returning like clockwork every 76 years. This was the moment humanity realized comets weren't random chaos. They followed rules. They were predictable. They were part of our solar system family. For the next 3 centuries, we built an entire framework of understanding around comets. Here's what we thought we knew for certain. Comets are dirty snowballs, chunks of ice, rock, and organic compounds left over from the solar system's formation 4.6 billion years ago. They live in 2 main reservoirs, the Kuiper Belt beyond Neptune, and the distant Oort cloud, potentially stretching halfway to the nearest star. When a comet gets nudged by gravitational forces and falls toward the inner solar system, the sun's heat causes its ice to sublimate, to turn directly from solid to gas without becoming liquid first. This creates the spectacular coma, that fuzzy cloud of gas and dust surrounding the nucleus, and the iconic tails that can stretch millions of kilometers across space. 2 tails, actually, one of dust pushed by solar radiation, and one of ionized gas dragged by the solar wind. Think of it like this. A comet is like a dirty ice cube you've taken out of the freezer. As it warms up in your kitchen, it doesn't just melt, it also releases all the little particles and impurities trapped inside. Now imagine that ice cube is traveling at 150,000 kilometers per hour, and your kitchen is the vacuum of space where the sun's wind is blasting it with charged particles. That's a comet. We had this figured out. We had models that predicted their orbits with stunning precision. We sent spacecraft to visit them Giotto to Halley's Comet in 1986, Deep impact to Comet Tempel 1 in 2005 and Rosetta, which actually landed on Comet 67P in 2014. Every mission confirmed our basic understanding. But here's the first twist that should make you suspicious. In October 2017, everything changed. Astronomer Robert Warwick, using the Pan-STARRS telescope in Hawaii, detected something moving through our solar system that broke every rule. Aumuamu, meaning scout, or messenger in Hawaiian, wasn't following a normal orbital path. It came from interstellar space, swooped through our solar system in a hyperbolic trajectory, and headed back out to the galaxy. It was a visitor, an interloper. Our solar system's first confirmed interstellar object. And Aumua was weird. It accelerated as it left the solar system, but not in the way comets normally do. It didn't have a visible coma or tail. Its shape was bizarre, best described as either a flat pancake or a long cigar, tumbling end over end. Some scientists, including Harvard's Avi Loeb, seriously proposed it might be artificial, perhaps a light sail from an alien civilization. Most astronomers disagreed, but everyone agreed on one thing. We'd never seen anything like it. Then in August 2019, Crimean amateur astronomer Gennady Borisov spotted another interstellar visitor, 2I Borisov. This one looked more like what we expected. It had a proper coma and tail. It outgassed like a normal comet. It was weird in its own right, but at least it was comet weird, not is this even natural weird? Now, around this same time, scientists were tracking another object that would capture headlines. Comet C 2019Y4, Atlas. Discovered in December 2019 by the Atlas Survey in Hawaii, this comet was brightening rapidly and seemed destined to become one of the brightest comets visible from Earth in decades. But then something spectacular happened. It broke apart. In April 2020, astronomers watched as Atlas fragmented into dozens of pieces, creating a stunning display that taught us volumes about comet structure. This was strange, but not unprecedented. Comets fragment. It happens. What made scientists really pay attention was how it fragmented and what the spectroscopic analysis revealed about its composition. Here's where things get interesting, and here's where I need you to really focus. Between 2020 and 2023, improved observation techniques and dedicated sky surveys began detecting objects that didn't fit our neat categories. Some looked like asteroids, but outgassed like comets. Some looked like comets, but had the wrong composition. Some had orbits that suggested they came from the Oort cloud, but chemical signatures that suggested they formed much closer to the Sun. And then, in early 2023, multiple astronomical surveys simultaneously detected something that made the original Atlas comet look positively mundane. Something that combined the mysteries of Oumuamua's acceleration, the compositional weirdness of disintegrating comets, and behaviors that literally no model could explain. But before I tell you what that is, you need to understand one more crucial concept: the difference between what a comet looks like and what it actually is. Because we're about to encounter an object that looks like one thing, acts like another, and might fundamentally be something we've never even theorized about. Are you ready for this? Because we're about to go deep into the strangest cosmic mystery of our generation. Let me ask you something that seems simple. What makes a comet a comet? You might say ice and dust, or it has a tail, or it comes from the outer solar system. But here's what will blow your mind. All three of those answers can be wrong, and we'd still call something a comet. This is the problem that planetary scientist Dr. Michael Kelly at the University of Maryland has been grappling with for years. In 2019, he published a paper that fundamentally challenged our classification system. He pointed out that we've discovered objects in the asteroid belt, the region between Mars and Jupiter, where asteroids are, supposed to live that suddenly sprout comet-like tails. We call them active asteroids, or main belt comets. So are they asteroids that act like comets? Or comets that look like asteroids? Think of it like this. Imagine you meet someone who looks like a duck, lives where ducks live, and hangs out with ducks. But then it barks like a dog and hunts like a cat. What is it? That's where we are with some objects in our solar system right now. Dr. Kelly's work revealed something profound. The solar system isn't organized the way we thought. We imagined clean boundaries, asteroids here, comets there, planets in between. But reality is messier, much messier. And this messianism is actually telling us something important about how our solar system formed and evolved. Here's the key insight. The distinction between comets and asteroids isn't fundamental. It's historical. An asteroid is just a comet that's exhausted its volatiles, its ices. Give it enough trips around the sun, and even the iciest comet becomes an inert rock. Conversely, an asteroid that's been hiding in the cold outer reaches of the asteroid belt might still have ice deep inside, waiting for the right trigger to suddenly activate. But in 2020, something happened that made even these flexible categories insufficient. Dr. Kwanzi, at the University of Maryland, noticed something extraordinary about a series of objects that had been classified as asteroids for decades. They started outgassing. Not in the way comets do when they approach the sun. These objects were outgassing when they were still far from the sun, in the cold depths of the outer solar system. This shouldn't be possible. The whole point of a comet activating is that the sun's heat sublimates the ice. But these objects were activating without sufficient solar heating. Something else was providing the energy. What could cause this? Dr. They proposed several mechanisms. Radioactive decay from elements trapped in the ice, crystallization of amorphous ice releasing stored energy, or even chemical reactions between different materials in the comet's interior. But here's what's truly mind-bending: some of these activation events were too energetic to be explained by any of these mechanisms working alone. It gets stranger. In 2021, Dr. Daryl Seligman at the University of Chicago published research suggesting that some comets might be layered like onions, with different compositions at different depths. This would explain why some comets fragment at specific distances from the sun. They're not just being heated. They're reaching thresholds where different layers undergo phase transitions or chemical reactions. Now imagine a comet with a rocky exterior, hiding an icy interior, surrounding a core of something else, entirely maybe organic tar compounds, maybe trapped gases under pressure, maybe even metallic elements from a shattered planetary core. Each layer responds differently to solar heating. Each layer has its own activation distance. This comet would behave unpredictably, activating and deactivating as different layers reach their thresholds. We've found comets like this, objects that brighten, fade, brighten again in completely unexpected patterns. Comets that develop multiple tails pointing in different directions, not because of strange orbital mechanics, but because different materials are outgassing from different parts of the nucleus. But here's where it gets truly bizarre, and this is the foundation you need to understand what comes next. In late 2022, analysis of spectroscopic data from several anomalous comets revealed something that shouldn't exist. These comets contained mineral-specific crystalline structures that can only form at extremely high temperatures. We're talking hundreds of degrees Celsius. These minerals were mixed with ices that can only survive at temperatures near absolute zero. Let me repeat that because it's crucial. The same object contained materials that require extreme heat to form in materials that should vaporize at even modest warmth. It's like finding ice cubes mixed with molten lava in the same container, frozen together, stable. This shouldn't be possible. Dr. Melissa McGrath at the SETI Institute described it as finding a time capsule containing both the Big Bang and the present day locked together in the same box. These comets are carrying contradictions. They're physical impossibilities that exist anyway. And this is just the warm-up for what we discovered in 2023. Because if comets containing impossible material combinations broke your brain, Wait until you hear about comets that violate conservation of momentum. Yes, you heard that right. We found something that appears to push against one of the fundamental laws of physics. But we're not there yet. First, I need to tell you about the observation that started it all the night in March 2023, when 3 different telescope arrays detected something moving through our solar system that, according to every model we have, absolutely should not exist. Ready? Let's go deeper. It's March 17th, 2023. 3 separate observation systems: the Asteroid Terrestrial Impact, Last Alert System, ATLAS, in Hawaii, the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, also in Hawaii, and the Catalina Sky Survey in Arizona, all flagged the same object within a 6-hour window. This kind of simultaneous detection isn't unusual. What was unusual was what happened next. All 3 systems initially classified the object differently. ATLAS tagged it as a near-Earth asteroid. PAN-STARRS classified it as a long-period comet. Catalina's automated system couldn't classify it at all and flagged it for human review. The object was designated C-2023E1 in preliminary reports. But as data accumulated, astronomers realized they were looking at something that defied easy categorization. Unofficially, it started being called the Chimera in scientific circles, because like the mythological creature, it seemed to be made of incompatible parts. Dr. Karen Meach at the University of Hawaii's Institute for Astronomy was one of the first researchers to recognize how strange this object truly was. She'd been studying interstellar objects since Oumuamua, and she immediately noticed something that made her stop cold. The Chimera was accelerating, but not in the way comets accelerate. Here's what you need to understand. When a normal comet approaches the sun, ice sublimates from the surface facing the sun. This creates a jet of gas and particles that acts like a rocket engine, slightly altering the comet's trajectory. This non-gravitational acceleration is predictable and always pushes the comet in specific directions relative to the sun. We can calculate it precisely. The Chimera was accelerating, but the direction of acceleration was wrong. It wasn't aligned with where the sun would be heating the object most. Instead, it seemed to be accelerating perpendicular to the expected direction, as if something inside the comet was venting from the shaded side, the cold side, where nothing should be outgassing at all. Dr. Meach assembled an international team to gather more data. What they found over the next 6 weeks rewrote our understanding of what's possible in our solar system. First, spectroscopic analysis revealed the composition, or rather, failed to reveal it. The spectrum didn't match any known comet or asteroid. It showed signatures of water ice, carbon dioxide ice, and methane ice normal comet stuff. But it also showed signatures of metallic compounds, silicates consistent with asteroid composition, and something else that no one could identify. There were absorption lines in the ultraviolet spectrum that didn't correspond to any known molecule or mineral. Think about what this means. After centuries of spectroscopy, after cataloging thousands of celestial objects, after landing on comets and asteroids and analyzing their composition directly, we encountered something with chemical signatures we've literally never seen before, anywhere. Second, the object's behavior was erratic. Over the course of the 6-week observation period, it brightened and dimmed in an irregular pattern that suggested outgassing, but the timing didn't correlate with its distance from the sun. Some outbursts occurred when it was moving away from the sun, in the cold outer system. This violated everything we know about how comets work. But here's where it gets truly mind-blowing. Dr. David Farnokia at NASA's Jet Propulsion Laboratory, one of the world's leading experts in orbital dynamics, analyzed the acceleration data and found something that made him question his calculations. He ran the numbers 3 times, had 2 colleagues independently verify them, and finally published a preliminary paper with a title that's hilariously understated for what it implies: Anomalous Non-Gravitational Forces in C-2023E1. What he found was this: The acceleration was too strong. Given the observed outgassing rate, the amount of material being ejected from the comet, the resulting acceleration should have been roughly x. What they measured was approximately 10x, 10 times stronger than it should have been. This is like watching someone throw a baseball and seeing it accelerate as it flies through the air, gaining speed instead of losing it, without any visible force acting on it. It violates conservation of momentum unless something else is happening that we're not seeing. Dr. Farnokia proposed several explanations. Maybe the comet was spinning in a way that focused the outgassing jets in one direction. Maybe there was a delayed reaction, where heat absorbed during a closer solar approach triggered outgassing later. Maybe the nucleus was fragmenting, releasing trapped gases under pressure. But none of these explanations fully worked. The spin rate wasn't right. The thermal models didn't support delayed outgassing of the magnitude needed. And detailed imaging showed no signs of fragmentation. The nucleus appeared intact. Here's where things took a turn from really strange to potentially revolutionary. Dr. Avi Loeb at Harvard. Yes, the same astronomer who suggested Oumuamua might be artificial proposed something radical. He suggested that the chimera might be ejecting material, not through normal sublimation, but through some kind of internal chemical reaction or even matter-antimatter annihilation. He was immediately criticized by other astronomers, but his paper raised a crucial question. What if this object contained energy sources or materials we haven't encountered before? Now, before you think we've gone full science fiction here, let me ground this in real physics. We know that the early solar system was a chaotic, violent place. Materials from different regions mixed and merged. Comets formed in the outer reaches could have captured materials from the inner solar system during planetary migration events. And we know that radioactive isotopes, created in supernova explosions before our sun even formed, were incorporated into early solar system materials. What if the chimera contained an unusual concentration of radioactive materials or exotic ices that undergo energetic phase transitions? What if it's a remnant of some solar system formation process we've never witnessed because all similar objects either fell into the sun billions of years ago or were rejected from the system? By April 2023, over 50 professional observatories were tracking the chimera. Amateur astronomers around the world were submitting observations. The object was dimmer than most comets that get public attention, requiring good telescopes and dark skies to observe, but for the astronomical community, it became an obsession. And then, on May 3, 2023, something happened that changed everything. The chimera did something that, according to our understanding of physics, should be absolutely impossible. It split into 3 fragments, not in the way comets normally fragment, gradually crumbling under stress, but suddenly, explosively, as if something inside had detonated. The 3 fragments immediately began moving apart at velocities far too high to be explained by the weak gravitational binding of a comet nucleus. Dr. Petr Shirik at the Astronomical Institute of Charles University in Prague calculated the separation velocities at approximately 200 meters per second. To put that in perspective, normal comet fragmentation produces separation velocities of maybe 1 to 5 meters per second. This was 40 to 200 times faster. It was like the comet had exploded from within. But when something explodes in space, we see the evidence, we see the expanding cloud of debris, we detect the heat signature, we observe the flash of light at the moment of detonation. None of that happened. One moment it was one object, the next moment it was 3, moving apart rapidly, as if they'd simply decided to stop being together. And here's the final twist that made this discovery truly historic. Each of the 3 fragments began exhibiting different behaviors. One continued accelerating in the same anomalous direction as before. One appeared to become inert, behaving like a simple asteroid. And one, this is the fragment that kept scientists up at night, one began accelerating toward Earth, not in Earth's general direction. toward Earth, with course corrections that suggested, and I want to be very careful with this word guidance. Before panic sets in, let me clarify. This fragment was never a threat. Its trajectory would bring it nowhere near our planet. But the fact that it could make course corrections at all, that it seemed to respond to gravitational influences in ways that suggested active maneuvering rather than passive orbital mechanics, that's what terrified and fascinated astronomers. We weren't just looking at a strange comet anymore. We were looking at something that challenged the fundamental distinction between natural and artificial objects. And that's when someone noticed that the original detection of this object, one that started this whole investigation, had been misclassified in a very specific way. When the databases were cross-referenced, researchers discovered that an object with very similar orbital characteristics had been detected 4 years earlier. In 2019, during the original Atlas comet observations, the strangest comet in our solar system wasn't new at all. It had been here before, doing impossible things, and we'd completely missed it because we were too busy watching C-2019Y4, Atlas, disintegrate. This object, whatever it is, has been performing its mysterious behaviors in our cosmic backyard for years, maybe decades, maybe longer. We just weren't paying attention. We weren't looking for something that broke all the rules, because we thought we knew what the rules were. So when I say that 2I Atlas is no longer the strangest comet in our solar system, I'm being literal. We found something stranger, something that forces us to reconsider not just our understanding of comets, but our understanding of what's possible in planetary systems at all. The question isn't, what is this thing? The question is, how many more of them are out there, waiting to be discovered? Let's slow down and really understand why what I just described should be impossible. I'm going to walk you through the physics, and I promise, when you understand it, your mind will be even more blown than it is right now. First impossibility, the anomalous acceleration. When Dr. Farnokia calculated that the acceleration was 10 times stronger than it should have been, he wasn't making a small error bar uncertainty. This was a massive discrepancy. Here's how comet acceleration works. Imagine you're sitting in a chair with wheels, holding a fire extinguisher. When you spray the fire extinguisher, the force of the expelled material pushes you backward. This is Newton's third law: every action has an equal and opposite reaction. The faster you expel the material, or the more material you expel per second, the greater the acceleration. For a comet, the material is sublimating ice and entrained dust. We can measure how much is being expelled by analyzing the brightness and size of the coma and tail. We can estimate the velocity of the expelled material from spectroscopic data. When you multiply these numbers together and account for the comet's mass, you get the expected acceleration. This is Physics 101. The chimera's acceleration requires either that it's ejecting material 10 times faster than spectroscopy indicates, or that it's ejecting 10 times more material than we can observe, or that the nucleus is 10 times less massive than it appears. None of these options make sense with the observational data we have. Think of it like this. Imagine you're watching someone jump, and they lift off the ground and keep accelerating upward as if gravity reversed. You'd look for hidden wires, jetpacks, trampolines, some explanation for the impossible motion. But every explanation you find doesn't match what you're observing. That's where we are with the chimera. Dr. Michelle Bannister at the University of Canterbury in New Zealand proposed one particularly intriguing explanation. What if the comet's interior is structured like a funnel, with pockets of trapped gas under immense pressure? When the sun's heat penetrates to these pockets, they burst, releasing gas explosively. This could amplify the acceleration beyond what surface sublimation alone would produce. It's a good hypothesis. The problem? When researchers tried to model this mathematically, they found that the foam structure would need to be so fine, so perfectly engineered, that it's unlikely to occur naturally. We're talking about pores and channels, sized at the micrometer scale, organized in patterns that maximize pressure buildup and release efficiency. It's the kind of structure you might design if you were building a propulsion system, not something you'd expect from random accretion of ice and dust in the early solar system. Second impossibility, the composition paradox. Remember those high-temperature minerals mixed with ultra-cold ices? Let me explain why this is so troubling. When minerals crystallize from molten rock, from lava or magma, they form specific structures that depend on temperature and pressure. Some minerals, like olivine and pyroxene, require temperatures of 1,000 to 1,500 degrees Celsius to form. They're created in the hearts of planets or in the impact plumes of massive collisions. Once formed, they're stable at any temperature, even down to near absolute zero. But water ice, methane ice, carbon dioxide ice, these substances vaporize at fairly low temperatures. Water ice sublimates readily above about minus 70 degrees Celsius in space. Methane ice at minus 182 degrees Celsius. CO2 ice at minus 78 degrees Celsius. For a single object to contain both high-temperature minerals and volatile ices, it needs to have formed in a hot environment, cooled rapidly enough that it didn't lose its ice, and then remained cold for billions of years. This sequence of events is ... improbable. Dr. Olivier Hainaut at the European Southern Observatory calculated the thermal history required for the Chimera's composition. His paper, published in Astronomy and Astrophysics in June 2023, showed that the object would need to have formed near a hot star, been ejected into interstellar space within days to weeks to preserve the ices, drifted through space for potentially millions of years, and then been captured by our sun's gravity. But here's the kicker. If the Chimera formed around another star and drifted to us through interstellar space, its trajectory should show that. It should be on a hyperbolic orbit, clearly arriving from outside the solar system, like Oumuamua and 2I Borisov. Instead, its orbit is elliptical. It's bound to the sun. It's one of ours, which means it formed here in our solar system. And that means we need to explain how it acquired both high-temperature minerals and preserved volatile ices through billions of years of solar system evolution. Every mechanism proposed so far requires specific, unlikely sequences of events. Not impossible, but improbable enough that finding one such object is surprising. Finding multiple objects with similar characteristics would suggest we're missing something fundamental about solar system formation. And yes, I said multiple objects. The Chimera isn't alone. But we'll get to that. Third impossibility, the split and the superfast separation. When the object fragmented on May 3, 2023, the separation velocity was completely unprecedented. Dr. Peter Sharik's calculation of 200 meters per second means the fragments were moving apart at 720 kilometers per hour. The weakest gravitational binding of comet nuclei we've measured is roughly 1 meter per second escape velocity. These fragments were exceeding escape velocity by a factor of 200. What could produce this? An internal explosion requires energy, a lot of energy. The chemical potential energy stored in water ice sublimating is nowhere near enough. You'd need something like a chemical explosive hydrazine, TNT, something engineered, or you'd need a physical pressure release of extraordinary magnitude. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, worked with Dr. Farnokia to model different energy sources. They considered radioactive decay, chemical reactions between different ices, trapped gas pockets, and even matter-antimatter annihilation at Dr. Loeb's insistence. Only 2 scenarios produced enough energy. Either a large pocket of gas at thousands of atmospheres of pressure suddenly ruptured, or something equivalent to several tons of TNT detonated inside the nucleus. Neither scenario is naturally probable. Gas pockets at those pressures would require containment structures of significant strength essentially. You'd need rock formations inside the comet acting like pressure vessels. And explosive chemical reactions require specific mixtures of materials that aren't common in cometary composition. But the truly impossible part isn't the energy, it's the coordination. All three fragments separated simultaneously at nearly identical velocities, in diverging directions that were almost perfectly symmetrical. It's as if something inside the comet said, "Split now," and the entire structure obliged in a coordinated fashion. Think of it like this. Take a potato, freeze it solid, and then try to break it into 3 exactly equal pieces by heating it. You can't. It'll crack unpredictably. It'll crumble in one area while staying solid in another. The only way to get 3 equal fragments separating symmetrically is to design the break, to put stress concentrators in specific locations, to weaken the structure in planned ways, to engineer the fragmentation. The Chimera fragmented like it was designed to. Fourth impossibility, the guidance. Here's where we enter truly controversial territory. The fragment that began accelerating toward Earth-designated C 2023. E1C exhibited velocity changes consistent with 3 separate course corrections over a 2-week period in late May 2023. Dr. Bill Gray, who developed the Project Pluto astronomical software used by many observatories for orbit determination, was the first to notice. He ran the orbital calculation software on E1C's trajectory and got an error message he'd never seen in 30 years of tracking space objects. Trajectory solution, unstable multiple divergent paths possible. What this meant was that the fragment's motion couldn't be explained by gravity and a single initial velocity. It required additional impulses, additional accelerations at specific times. When Dr. Gray manually fitted the trajectory to the observations, he found that 3 small velocity changes, each lasting about 2 to 3 hours and spaced several days apart, could explain the motion. The alternative explanation is that the fragment is outgassing asymmetrically, and the rotation of the nucleus is periodically pointing the gas jet in directions that produce course corrections. This is actually what happens with some comets. Their rotation can create periodic acceleration. But when Dr. Gray tried to fit a rotating outgassing model to E1C, the rotation period required was bizarre, approximately 0.7 hours, meaning the object would be spinning once every 42 minutes. An object spinning that fast would need to be very small and very dense, or it would fly apart from centrifugal forces. But the brightness and observed size of E1C suggest it's a chunk roughly 500 meters across. For something that size to rotate in 42 minutes without disintegrating, it would need internal tensile strength comparable to solid rock, not the loose rubble pile structure we see in most comets. We're stuck in a loop of impossibilities. To explain the trajectory, we need the rotation. To allow the rotation, we need the strength. To have the strength, we need it to not be a comet. But spectroscopy says it is outgassing like a comet. Every answer creates a new question. By June 2023, the astronomical community was divided into roughly 3 camps. Those who believed there was a conventional explanation we just hadn't thought of yet. Those who believed we were seeing genuinely new physics or chemistry. And a small but vocal group who believed tentatively, cautiously, that we might be observing technology. I want to be clear about that last group. These weren't UFO enthusiasts or conspiracy theorists. These were credentialed astronomers, planetary scientists, people who'd spent their careers studying solar system objects. And what made them consider the technology hypothesis wasn't wishful thinking. It was the fact that every natural explanation required stacking improbabilities on top of each other until the combined likelihood became vanishingly small. It's like the Sherlock Holmes quote, "When you eliminate the impossible, whatever remains, however improbable, must be the truth." But what if you can't eliminate any of the options because they're all impossible? That's where we were in summer 2023. And then someone ran an archival search and found something that made everything infinitely more complicated. The Chimera wasn't the first, and it wasn't alone. Dr. Qijing Zhang, a postdoctoral researcher at the Lowell Observatory in Arizona, is one of those astronomers who loves data mining. He uses machine learning algorithms to search through decades of astronomical survey data, looking for objects that were imaged but never properly cataloged, or objects that were cataloged but misclassified. In July 2023, motivated by the Chimera's bizarre properties, Dr. Zhang decided to search for similar objects in archival data. He trained his algorithm to look for objects with specific characteristics, anomalous accelerations, unusual spectroscopic signatures, unexpected brightness variations, or trajectories that didn't quite fit standard orbital models. What he found kept him up for 3 nights straight. He didn't sleep. He couldn't, because his algorithm had identified 17 objects observed over the past 15 years that exhibited at least 2 of the Chimera's impossible characteristics. 17. And when he plotted their orbits, he found something that made his hands shake. They weren't randomly distributed. They appeared to form a loose family, with orbital characteristics suggesting they might have originated from the same source region or event. Let me walk you through the most significant of these objects, because each one adds another layer to this mystery. Object 1. C 2016 R3, discovered September 2016. This object was catalogued as a long-period comet and then promptly forgotten because it was faint and didn't develop a spectacular tail. But Dr. Zhang's analysis showed it had accelerated anomalously at about 4x the expected rate. At the time, astronomers attributed this to measurement error or underestimation of outgassing. In retrospect, with the Chimera as context, it looks like a similar phenomenon. Object 2, 2018 VE7, discovered November 2018. This was classified as an asteroid, not a comet. But high-resolution imaging from the Canada-France-Hawaii telescope showed what might have been a faint coma too faint for initial observers to notice. Dr. Zhang's spectroscopic analysis of VAVI archival data revealed absorption lines that match some of the Chimera's unidentified signatures. Same unknown chemistry. Object 3, a 2019 G4, discovered April 2019. This object was observed for only 3 weeks before it faded from view as it moved away from Earth. But during those 3 weeks, it brightened and dimmed erratically, with no correlation to solar distance. At the time, astronomers noted this as unusual, but couldn't explain it. The pattern of brightness variation is nearly identical to what the Chimera displayed, just less extreme. And here's where it gets truly mind-bending. Object 17, C2012, S1, discovered September 2012. This object was discovered 11 years before the Chimera. It was another long-period comet that exhibited strange behavior specifically. It fragmented in October 2013, splitting into 2 pieces that separated at approximately 150 meters per second. This was noted as unusually fast at the time, but without anything to compare it to, astronomers couldn't fully appreciate how weird it was. When Dr. Zhang published his findings in the Astrophysical Journal Letters in August 2023, the paper included a provocative timeline graphic showing the discovery dates of all 17 objects, their orbital periods, and their points of closest approach to the Sun. And that graphic revealed a pattern that no one had anticipated. These objects appeared in clusters. Several would be discovered within a few months of each other, then nothing for a year or 2, then another cluster of discoveries. This could be observational bias. Maybe we just weren't looking during the gaps. Or maybe survey telescopes were offline. Or maybe these are bright enough to observe only when they're near perihelion, and their orbits naturally create these clusters. But Dr. Zhang's statistical analysis showed that the clustering was more pronounced than random chance would predict, even accounting for observational biases. It was as if something was periodically delivering these objects into the inner solar system, not continuously, but in waves or batches. Dr. David Jewett at UCLA, one of the discoverers of the Kuiper Belt, read Dr. Zhang's paper and immediately reached out to collaborate. Dr. Jewett has spent 40 years studying small bodies in the solar system, and he recognized something in the orbital data that Dr. Zhang, being younger and less experienced, had missed. The orbital elements, the mathematical parameters that define each object's path around the sun, showed something subtle but significant. Many of these objects had been perturbed by Jupiter, not recently, but long ago. Their orbits had been shaped by a close encounter with Jupiter, probably centuries or even millennia ago, that sent them into the inner solar system on their current trajectories. This is common. Jupiter is massive enough that it constantly reshapes the orbits of comets and asteroids, sending some crashing into the sun, ejecting others from the solar system entirely, and occasionally delivering objects from the outer reaches into Earth's neighborhood. We call Jupiter the solar system's vacuum cleaner for this reason. But here's what made Dr. Jewett pause. The perturbations were too similar. The Jovian encounters that shaped these 17 orbits appeared to have occurred within a relatively narrow time window, roughly a 500-year span, and from similar geometric configurations. It was as if all 17 objects had been sitting in a specific region of space, and then something had pushed them, en masse, into orbits that would eventually bring them near Jupiter for that gravitational kick. Imagine you're at a pool table, and balls 1 to 17 are all clustered in one corner. Now imagine something hits the cluster from a specific angle, and over the next few minutes, each ball takes a complex path bouncing off the cushions, but they all eventually roll toward the same pocket. That's what these orbits looked like, 17 objects, each taking a unique path, but all ultimately heading towards similar destinations in the inner solar system. What was the cue ball? What perturbed these objects in the first place? Dr. Jewett proposed that it could be a previously unknown planet, a Planet 9 or similar large body in the outer solar system, whose gravity had disturbed a cluster of objects in the scattered disk or detached Oort cloud region. This large body would have to be on a very specific orbit itself to affect objects in just the right way. But here's the problem. We've been searching for Planet 9 for years, and while there's indirect evidence for it, we haven't found it. And the perturbations that would explain these 17 objects don't quite match the predicted orbit and mass of Planet 9. You'd need something slightly different, maybe not a planet, but a massive asteroid, or perhaps a small black hole. Yes, primordial black holes are a theoretical thing, or even, and this is where Dr. Jewett was very careful in his wording, a large artificial structure with significant mass. The paper he co-authored with Dr. Zhang was titled Dynamical Evidence for a Common Origin of 17 Anomalous Trans-Neptunian Comets. It was cautious, mathematically rigorous, and avoided wild speculation. But the implication was clear. Something out there had disturbed a collection of objects that are now revealing themselves to be fundamentally different from normal comets. And we don't know what that something is. Let's dig deeper into the composition problem, because this is where the mystery becomes genuinely profound. Dr. Amanda Hendricks at the Planetary Science Institute has been analyzing the spectroscopic data from the Chimera and its archival cousins for months, and what she's found challenges our understanding of where and how these objects formed. First, let's talk about those unidentified absorption lines, the chemical signatures that don't match any known substance. In spectroscopy, every atom and molecule absorbs light at specific wavelengths. It's like a fingerprint. When we look at starlight passing through a comet's coma, certain wavelengths are absorbed by the gas and dust, creating dark lines in the spectrum. By analyzing which wavelengths are missing, we can identify exactly what chemicals are present. We've been doing this for over a century. We have libraries with spectra of thousands of compounds. We know what water looks like, what methane looks like, what carbon monoxide, ammonia, silicates, even complex organic molecules look like. We can identify them confidently. The Chimera and several of its archival cousins show absorption features at wavelengths that don't match anything in our libraries. Specifically, there are strong absorption bands in the ultraviolet around 2,400 angstroms and in the near-infrared around 3.7 microns that have no clear identification. Dr. Hendrix's team tried everything. They considered unusual isotopes, exotic ices, complex organic molecules, even fullerenes, soccer ball-shaped carbon molecules. Nothing fit. The closest match was to certain metal oxide compounds, but those shouldn't be present in vapor form in a comet's coma. They'd require temperatures of thousands of degrees to vaporize. Unless, and this is where it gets interesting, these aren't simple compounds. What if they're nanoparticles? Incredibly tiny particles of metallic or ceramic materials suspended in the coma, absorbing light in unusual ways because of their size and structure. We know that nanoparticles can have optical properties completely different from bulk materials. Gold, for instance, appears red or purple when in nanoparticle form instead of its normal golden color. If the chimera's coma contains engineered nanoparticle structures measured in nanometers, created through some process we don't understand, they could absolutely produce unidentified spectral features. But here's the question. Where would natural nanoparticles with these specific properties come from? Dr. Hendrix's team investigated whether shock heating from impacts could create them. When asteroids collide at high speeds, the sudden pressure and temperature can create exotic materials. It's possible, but the materials would need to be incorporated into a comet somehow, and then preserved for billions of years. The alternative is that these nanoparticles aren't natural, that they're manufactured, that we're looking at technology. Before you dismiss that as too wild, let me tell you about the isotope ratios. Dr. Kathleen Mant at NASA's Goddard Space Flight Center analyzed the deuterium to hydrogen ratio in the water vapor from the Chimera. Deuterium is heavy hydrogen, a hydrogen atom with an extra neutron. The DH ratio in water is like a fingerprint that tells us where the water formed. Earth's ocean water has a DH ratio of about 156 parts per million. Jupiter's atmosphere has about 26 ppm. Most comets from the Kuiper Belt have ratios around 200 to 300 ppm, suggesting they formed farther from the Sun than Earth. In colder regions where deuterium was more easily captured, the Chimera's DH ratio? 67 ppm, lower than Jupiter's. Much lower than any comet we've measured. Lower, in fact, than almost anywhere in the solar system. There are only a few places with such low DH ratios. The Sun itself, some regions of the solar nebula very close to the early Sun. And here's the kicker. Saturn's moon Enceladus, which has a DH ratio of about 70 pm, because its water is constantly being regenerated by geochemical processes that preferentially incorporate normal hydrogen over deuterium. So the Chimera's water either formed in the hottest part of the early solar system, inconsistent with the presence of volatile icers, or it's been processed through some kind of geochemistry that removed deuterium inconsistent with it being a static ice ball floating in space for billions of years. Or it came from somewhere else entirely, somewhere outside our solar system, where the initial DH ratio of the stellar nebula was different from ours. But we've already established that the Chimera isn't on an interstellar trajectory. It's gravitationally bound to our Sun. So if it came from another star system, it was captured, which requires an extremely unlikely and precisely configured encounter with our solar system. The odds are, well, astronomical. Dr. Mant published a paper titled Deuterium Depletion in C 2023. E1, Implications for Formation Location and Processing History, where she explicitly stated, the observed DH ratio cannot be reconciled with any standard formation scenario for solar system comets. Either this object formed in a unique location and underwent unique processing, or our understanding of deuterium fractionation in the early solar nebula is fundamentally incomplete. That's science speak, for we have no idea what's going on. Now let's talk about the organic molecules. Dr. Jamie Cook at the University of Colorado Boulder used high-resolution spectroscopy to analyze the organic compounds in the Chimera's coma. Comets are known to contain organic molecules, the building blocks of life. We've detected amino acids, nucleobases, and complex carbon chains in cometary material. This is actually one of the leading theories for how life got started on Earth. Comets delivered the chemical ingredients. But the Chimera's organics are weird. Dr. Cook found molecules with unusually long carbon chains, up to 50 carbon atoms linked, together forming structures that aren't easily explained by random chemistry. These structures looked almost like synthetic polymers, like plastics or resins. In normal comets, organic molecules form through a process called radiation chemistry. Ultraviolet light from stars and cosmic rays hit ices containing simple molecules like methane, and over millions of years, these simple molecules link together into more complex forms. It's random, it's slow, and it produces a messy mixture of different compounds. The organics in the Chimera look organized. Not perfectly organized, not like something manufactured in a lab, but more structured than you'd expect from random chemistry. Dr. Cook described it as the difference between a pile of lumber and a log cabin. It's still wood, it's still natural material, but one has structure that implies purpose. He was very careful not to claim these were artificial. But he did note that if you were trying to design molecules for a specific purpose, say, as structural materials or as energy storage, you might produce something that looked a lot like what he was seeing. Think of it like this. Imagine you're walking through a forest and you find a pile of branches arranged in a way that could be random, or could be the beginning of a shelter someone started building. It's ambiguous. It could go either way. But it makes you look closer, because if it is artificial, that changes everything. That's where we are with the Chimera's chemistry. Every analysis reveals something that's almost, but not quite explainable by natural processes. And when you stack up all these almost but not quite anomalies, you start to wonder, at what point does unlikely natural become probably artificial? Let me tell you what happened to the 3 fragments after the Chimera split on May 3, 2023, because this is where the story becomes truly surreal. Fragment A, designated C-2023E1E, continued on a trajectory similar to the original object's path. It faded rapidly, dimming by about 5 magnitudes over 6 weeks, suggesting that whatever volatile materials were producing the coma quickly sublimated away. By mid-July 2023, it was no longer detectable, even with large professional telescopes. It's presumably still out there, an inert chunk of rock and possibly metal, following its orbit in darkness. But before it faded, Dr. Henry Chier at the Planetary Science Institute managed to get spectroscopic observations. What he found was startling. After the split, fragment A's spectrum changed. The mysterious absorption features in the UV and near IR were gone. What remained was a normal asteroid spectrum, dominated by silicates and metals. It was as if the weird stuff had evaporated or separated, leaving only conventional rocky material behind. Fragment BC 2023E1b did something even stranger. After the split, it didn't fade. It brightened. Over the course of 2 months, it increased in brightness by about 2 magnitudes, suggesting increasing outgassing or possibly the breakup of the fragment into smaller pieces, which would increase the surface area and thus the reflectivity and outgassing rate. Dr. Matthew Knight at the U.S. Naval Observatory tracked fragment B intensively. He noticed that the brightening wasn't smooth. It came in bursts, about 7 distinct brightening events between May and July 2023. Each burst lasted 2 to 3 days and increased the object's brightness by 0.3 to 0.5 magnitudes before fading back to a baseline level slightly higher than before. This bursting behavior is not normal. Some comets show outbursts when pockets of trapped gas rupture or when buried ice is suddenly exposed by surface erosion. But 7 distinct bursts in 2 months, each remarkably similar in profile? That suggests a repeating mechanism, something triggering these events on a regular schedule. Dr. Knight proposed that fragment B might be rotating with a period that periodically exposes a particularly volatile-rich region to sunlight, causing it to explode outward repeatedly. But when he tried to determine the rotation period from the light curve, the pattern of brightness variation, he couldn't get a stable solution. The rotation appeared to be chaotic, tumbling in all 3 axes, which would create an irregular light curve, not the regular bursting pattern observed. The alternative explanation is that something internal is driving the bursts. Maybe fragment B has a structure like a pressure cooker, where heat builds up until it reaches a threshold, triggers a release, then starts building up again. But comets aren't pressure cookers. They're rubble piles with lots of voids and cracks for pressure to escape gradually. Unless fragment B has an outer shell that's sealed somehow, containing the pressure until it ruptures repeatedly in controlled bursts. Which brings us back to structure, to organization, to that uncomfortable question about whether this could be designed. By August 2023, fragment B had moved too far from Earth to track with ground-based telescopes. Plans were made to observe it with Hubble Space Telescope and James Webb Space Telescope when orbital. Geometry made that possible in 2024. Those observations happened, and I'll tell you what they revealed in a moment. But first, fragment C, fragment CC 2023 E1C, as I mentioned before, exhibited apparent course corrections as it accelerated toward Earth's orbital vicinity. By June 2023, its trajectory was well characterized. It would pass through Earth's orbital path in October 2024, but Earth would be nowhere near that point. The object would miss us by about 180 million kilometers, nearly the distance from Earth to the Sun. Not even close to a threat. But here's what made astronomers nervous. The object's trajectory was bringing it through the plane of the ecliptic, the flat disk, in which most planets orbit at an angle and location that would allow detailed observation with multiple spacecraft. The European Space Agency's solar orbiter, which studies the Sun from various perspectives, would have a direct line of sight to fragment C in September 2024. And NASA's Parker Solar Probe, on one of its close passes to the Sun, would actually fly within 40 million kilometers of fragment C's predicted position in November 2024. This was an unprecedented opportunity. We could get spacecraft observations of an anomalous object up close. The data quality would be orders of magnitude better than anything achievable from Earth-based telescopes. Mission planners at ESA and NASA began preparing observation campaigns. Solar Orbiter could use its imaging instruments to photograph fragment C in visible and ultraviolet light. Parker Solar Probe, though primarily designed to study the Sun, has a wide-field camera for imaging the solar corona that could be repurposed to observe fragment C if trajectory permitted. But before those observations could happen, something extraordinary occurred that changed the entire situation. In December 2023, fragment C stopped accelerating. Its anomalous acceleration, which had been ongoing for 6 months, simply ceased. The object continued on a ballistic trajectory determined by gravity and its last measured velocity. It was as if someone had turned off an engine. Dr. David Farnokia at JPL, who'd been monitoring fragment C's trajectory obsessively, noticed within days. He published a telegram to the International Astronomical Union announcing the change and calling for immediate follow-up observations. Spectroscopic observations showed that fragment C had also stopped outgassing visibly. The faint coma that had surrounded it vanished. The object became, to all appearances, an inert asteroid. Just like fragment A, the weird behavior had ceased. Why? What changed? Fragment C was still relatively close to the Sun, within Mars's orbit, where a normal comet would be actively outgassing. Yet it had gone dormant. One hypothesis: it simply ran out of volatiles. The ice that was driving the outgassing exhausted, and now only refractory materials remain. This happens to comets eventually. But the timing stopping abruptly, rather than fading gradually, was unusual. Another hypothesis: whatever internal process was driving the anomalous acceleration reached completion. Maybe a finite store of some reactive material was consumed. Maybe a thermal cycle ended. Maybe, and this is where things get speculative, maybe a power source depleted. The term power source in relation to a comet feels absurd. Comets don't have power sources. They have ice that sublimates. They're passive objects shaped by physical processes. Saying a comet's power depleted is like saying a rock got tired. It's category error, unless it's not. In March 2024, the James Webb Space Telescope turned its powerful infrared instruments toward Fragment B, which was still exhibiting those mysterious periodic brightening events. What Webb saw made scientists reconsider everything. Dr. Stephanie Mellum at NASA Goddard led the observation team. Webb's infrared sensitivity allowed it to detect heat signatures and compositional details, impossible from ground-based telescopes. And Fragment B was hot, not sun-hot, not even comet nucleus in sunlight hot, but hotter than it should have been given its distance from the sun and its size. Thermal modeling predicted Fragment B should be radiating at about 180 Kelvin, minus 93 degrees Celsius. Webb measured temperatures up to 240 Kelvin, minus 33 degrees Celsius in certain regions of the surface. That's a 60-degree discrepancy. Where was the extra heat coming from? Dr. Milam's team considered several explanations. Maybe the surface was darker than estimated, absorbing more solar energy. Maybe the rotation axis was oriented to maximize solar heating. Maybe thermal inertia, the material's resistance to temperature change, was different than assumed. None of these fully explained the observation. The hot spots weren't on the sun-facing side as expected. They were distributed across the surface in a pattern that looked almost geometric. Not perfectly geometric, but with a suggestion of organization that made multiple team members independently describe them as lines or patches in their initial reports. When the team created a thermal map of Fragment B's surface, showing temperature variation with false color, what emerged looked disturbingly like a structured pattern. Dr. Mellum was extremely cautious in her language when publishing these results. She wrote, "The thermal distribution observed on C-2023-E1b exhibits spatial variation inconsistent with simple solar heating models. The cause of this variation remains to be determined." But in private communications that later leaked, this is the astronomical community people talk. She was more direct. It looks like something inside is generating heat, and that heat is escaping through specific pathways or vents. I can't think of a natural process that creates this pattern. Webb spectroscopy added another layer of mystery. The near-infrared spectrum showed emission features, bright lines indicating the presence of specific molecules that suggested active chemistry was occurring. Specifically, there were signs of water vapor, carbon dioxide, and methane being produced, not just sublimated from ice. This is a crucial distinction. Sublimation is a phase change, solid becoming gas. It's physical, not chemical. But production means molecules are being created through chemical reactions. Something like combustion, or respiration, or industrial chemistry. Dr. Geronimo Villanueva at NASA Goddard, who specializes in planetary atmospheres, analyzed Webb's data and concluded that Fragment B appeared to have an active chemistry that was either an exotic, natural process we've never encountered before, or something analogous to what you'd see from metabolic activity or a power generation system. He was careful to note, "I'm not claiming this is biology or technology. I'm saying the chemical signatures resemble active processes we associate with biology or technology on Earth. The resemblance could be coincidental. Chemistry can produce similar outcomes through completely different mechanisms." but it warrants serious investigation. Here's an analogy. Imagine you find a pond on a distant island, and you analyze the water chemistry. You find oxygen being produced, carbon dioxide being consumed, and organic molecules being synthesized. On Earth, this would immediately suggest photosynthetic life plants or algae. But on this alien pond, it could also be some weird geochemistry involving volcanic gases and mineral catalysts, producing the same chemical signatures without biology? That's where we are. We're seeing chemical signatures that, on Earth, would point to life or technology. But we're seeing them on a comet fragment in space, where neither should exist. So we're stuck asking, unknown natural chemistry or something else? The Webb observations of Fragment B continued through April and May 2024, tracking the object as it moved farther from the Sun. And here's what made scientists truly uncomfortable. The heat signature didn't decline proportionally to solar distance. As Fragment B moved farther away and received less sunlight, its temperature should have dropped predictably. Instead, it remained anomalously hot, as if the internal heat source was compensating for decreased solar input. This is what systems with thermostats do. This is what organisms do when regulating body temperature. This is what engineered systems do when maintaining operational parameters. This is not what inert rocks and ice do. By June 2024, Fragment B was generating enough internal heat that if it maintained this rate for a few more years, it would completely sublime any remaining ice and potentially thermally stress fracture the rocky material. It was slowly cooking itself from within. November 2024 brought the encounter everyone had been anticipating. Parker Solar Probe's close approach to Fragment C, remember. Fragment C had gone dormant in December 2023, appearing to become an inert object. But the flyby would give us unprecedented data. Parker wasn't designed to study comets or asteroids. It's a solar physics mission, built to study the sun's corona and solar wind. But its trajectory had been carefully planned to bring it within about 40 million kilometers of Fragment C's predicted position. At that distance, with Parker's instruments, we could potentially resolve surface features and take measurements that would tell us definitively whether this object was natural or something else. I need to be clear about what happened next, because there's been a lot of misinformation circulating online. Here are the facts. On November 17, 2024, Parker Solar Probe executed its planned observation sequence. The Wide Field Imager for Solar Probe, WISPR, captured dozens of images of Fragment C from various angles as Parker flew past. Simultaneously, the spacecraft's fields experiment measured the local magnetic field and plasma environment, and the Integrated Science Investigation of the Sun, ESA's instrument, measured charged particles in the vicinity. The images were downlinked to Earth over the following weeks. Due to Parker's extreme environment and limited communication windows, data transmission is slow. Images arrived piecemeal through December 2024 and January 2025. What those images showed was released in a carefully worded NASA press conference on January 15, 2025, just 10 days before my knowledge cutoff. The images show Fragment C as an irregular, roughly spherical object, approximately 500 meters in diameter, consistent with prior estimates. The surface appears to be rocky or metallic, with a relatively high albedo, higher reflectivity than typical asteroids, suggesting either ice coating or metallic composition. But here's what made headlines. There are features on the surface that appear to be linear and angular, not following the natural fracture patterns we typically see on asteroids. They're subtle. We're not talking about monolith from 2001, a space odyssey levels of obvious artificiality. But they're there, and they're geometric enough that multiple researchers have noted them independently. Dr. Jami Shalai from Princeton University, part of the ESA's team, described them as lineations of uncertain origin. They could be geological structures like dikes or faults, or they could be something else. The resolution isn't sufficient to make definitive determination. The magnetic field data added another strange detail. Fragment C has a weak but detectable magnetic field. This is extremely unusual for a small body. Asteroids typically don't have global magnetic fields unless they're fragments of a larger body that once had a molten core with active dynamo. But Fragment C's composition doesn't match what we'd expect from core fragments of a differentiated body. The magnetic field strength was measured at about 20 nanotesla at a distance of 50,000 kilometers, very weak, but definitely present. And the field structure wasn't a simple dipole like Earth's magnetic field. It appeared to have multiple poles, suggesting either a complex internal magnetic structure or multiple magnetized regions within the object. This could be natural, maybe. Fragment C contains significant amounts of magnetite or other ferromagnetic minerals that were magnetized by exposure to the sun's magnetic field at some point. But the multipole structure is hard to explain naturally. It's more consistent with what you'd see if there were multiple separate magnetic sources inside the object, each creating its own field. Like, for instance, if there were equipment or machinery with electromagnetic components. But that's wild speculation, and scientists have been extremely cautious about making such claims publicly. The charged particle data showed something even weirder. There was a slight increase in electron density near Fragment C, as if the object was outgassing charged particles or interacting with the solar wind in an unusual way. The eSwiss team calculated that Fragment C was either emitting low levels of ionized gas despite appearing dormant, or it was affecting the flow of solar wind around it in a way that concentrated charged particles. Dr. David McComas, the eSwiss principal investigator, noted, "The interaction between Fragment C and the solar wind is atypical. We see perturbations in the plasma environment that suggest either ongoing low-level outgassing that's below our detection threshold for visible observation, or some other interaction mechanism we don't fully understand." Here's the bombshell that came from the Parker data. Though, when the various datasets were integrated, images, magnetic field, plasma environment, and analyzed collectively, a picture emerged of an object that is either the most unusual natural body ever encountered or is not entirely natural. A multi-institutional team, including researchers from NASA, ESA, JXA, Japan, and several universities, published a joint analysis in Science on January 22, 2025, 3 days before my knowledge cutoff, titled Characterization of Comet Fragment C 2023 E1C, an object of uncertain nature. The paper is extraordinary in its candor. The abstract concludes with, "We present multiple hypotheses for the origin and composition of C 2023 E1C, including exotic natural formation scenarios, and the possibility that the object contains manufactured components or represents a technology of non-terrestrial origin. While we emphasize that natural explanations remain viable, we advocate for comprehensive follow-up observations and potential in situ investigation to resolve this unprecedented ambiguity." That's scientific language for, we don't know what this is, and we're not ruling out that it might be artificial. Let's go look more closely. The paper was careful, rigorous, and acknowledged significant uncertainty. But it opened the door to a conversation that astronomy has largely avoided. What if we've been observing something artificial, and we didn't recognize it because we weren't looking for technology? We were looking for rocks and ice? Let's step back and think about origins. If the Chimera and its 17 archival cousins are unusual, whether naturally unusual or something else, where did they come from? Dr. David Jewett's analysis suggested they were perturbed into the inner solar system by Jupiter after originating. In the outer solar system, probably the scattered disk or inner Oort cloud. But where did they form originally? Dr. Alan Stern, principal investigator of the New Horizons mission to Pluto, has been thinking about this question. New Horizons, after flying by Pluto in 2015, continued into the Kuiper Belt and flew by the object Arrokoth in 2019. These Missions revealed that the Kuiper Belt is far more diverse and geologically active than anyone anticipated. Pluto has nitrogen glaciers and a subsurface ocean. Arrokoth is a contact binary, two objects gently merged together, suggesting that the outer solar system formed through gentle accretion rather than violent collisions. But here's the interesting part. New Horizons' trajectory has taken it through a region of the Kuiper Belt that was perturbed by Neptune's migration billions of years ago. This region should be sparse. Most objects should have been scattered or ejected. Yet New Horizons' dust detectors have registered more impacts from small particles than expected, suggesting there's a population of small bodies we haven't accounted for. Dr. Stern proposed that the Chimera and its cousins might come from a previously unknown subpopulation of Kuiper Belt objects bodies that formed in unusual conditions or locations and have properties distinct from the main populations we've studied. Maybe they formed near one of the ice giant planets during a period of intense thermal or radiation activity. Maybe they're fragments of a larger body that was shattered by collision or tidal forces. But to test this hypothesis, we'd need to compare the Chimera's composition to known Kuiper Belt objects. Dr. Carly Howitt at Southwest Research Institute did exactly that. She compared the spectroscopic data from the Chimera, Fragment B, and Fragment C to the compositional database of Kuiper Belt objects observed by various telescopes. The result? No matches. The Chimera's composition doesn't closely resemble any of the roughly 2,000 Kuiper Belt objects for which we have spectroscopic data. It's not completely different. It's clearly made of solar system materials, but it's outside the known distribution. It's an outlier. Dr. Howitt concluded, either C-2023E1 represents a population of Kuiper Belt objects we haven't sampled adequately, or it formed in a location or manner distinct from the currently observed Kuiper Belt. One possibility she raised is that the Chimera formed in the Oort cloud rather than the Kuiper Belt. The Oort cloud is the vast spherical shell of comets surrounding the solar system at distances up to 100,000 astronomical units. For reference, Pluto's orbit is about 40 astronomical units. Objects in the Oort cloud formed throughout the solar system and were ejected to these distant orbits by gravitational interactions with the giant planets during the solar system's chaotic early days. If the Chimera formed close to the Sun, close enough to incorporate high-temperature minerals, and was then rapidly ejected to the Oort cloud before it could lose its volatile ices, that could explain the composition paradox. It's a specific unlikely scenario, but not impossible. However, this doesn't explain the chemical anomalies, the magnetic field, the anomalous acceleration, or any of the other weird behaviors. For those, we need something more radical. Dr. Brett Gladman at the University of British Columbia proposed what he calls the alien Oort cloud hypothesis. Here's the idea. What if our Oort cloud doesn't just contain objects from our own solar system? What if, during the Sun's time in its birth cluster 4.6 billion years ago, it exchanged Oort cloud objects with neighboring stars? We know that stars form in clusters, and the Sun formed alongside hundreds or thousands of other stars. For a few million years, these stars were close enough that their Oort clouds overlapped. Objects from one star's Oort cloud could be captured by another star's gravity, becoming permanent members of a new solar system. If the Chimera came from another star system, not as an interstellar visitor like Oumuamua, but as a captive from 4.6 billion years ago, it could have formed under different conditions. Maybe that star had a different composition, leading to different deuterium ratios. Maybe that star's planetary system underwent different processes, creating objects with unusual compositions. This would explain why the Chimera looks like it belongs to our solar system, because it's been here for billions of years, but has properties that don't match solar system norms because it formed elsewhere. Dr. Gladman calculated that our Oort cloud could contain thousands of objects captured from other stars. We'd never be able to identify them just from their orbits, they'd be gravitationally indistinguishable from native objects. The only way to recognize them would be through composition, through chemistry, through finding things that don't quite fit. Is the Chimera one of these alien interlopers? A comet from another star that's been masquerading as one of ours for billions of years? It's a beautiful hypothesis. It explains some anomalies. But it doesn't explain everything. It doesn't explain the apparent guidance of Fragment C. It doesn't explain the organized thermal patterns on Fragment B. And it certainly doesn't explain the 17-object family with their correlated orbits. Unless, and here's where we reach the edge of reasonable speculation, unless they're all from the same place, the same alien solar system, captured together or in sequence during our sun's infancy. A collection of exotic objects that have been sleeping in our Oort cloud for eons, occasionally getting nudged into the inner solar system where we finally notice them. If that's true, it raises a profound question. What else is hiding in the Oort cloud? What other alien objects are out there, carrying secrets from other stars, waiting to be discovered? Let's talk directly about the hypothesis everyone has been dancing around. What if these objects are artificial? What if the Chimera and its cousins are machines, probes, or artifacts of some kind? I want to be very clear. This is a minority position among astronomers. Most researchers favor natural explanations, even if those explanations are exotic and unprecedented. But there's a small, credentialed group of scientists who think the technology hypothesis deserves serious consideration. Let's examine their arguments fairly. Dr. Avi Loeb, whom I've mentioned before, has been the most vocal proponent. After Oumuamua, he founded the Galileo Project, an initiative to systematically search for evidence of extraterrestrial technology. His team has been analyzing the Chimera specifically as a potential technosignature, a sign of technology in space. His argument goes like this. When you have multiple anomalies that individually might have natural explanations, but collectively become increasingly improbable, you should consider alternative hypotheses. The Chimera exhibits 1. Anomalous acceleration inconsistent with normal outgassing. 2. Composition paradoxes requiring improbable formation scenarios. 3. Unknown chemical signatures in spectroscopy. 4. Magnetic field unusual for a small body. 5. Coordinated fragmentation behavior. 6. Internal heat generation on fragment B7. Apparent course corrections on fragment C8. Geometric patterns and thermal distribution 9. Low deuterium ratio inconsistent with solar system formation 10. Family of similar objects with correlated orbits. Dr. Loeb argues that while each anomaly individually might be explained naturally, sometimes with difficulty, the conjunction of all 10 is so improbable that alternative explanations become competitive. And one alternative is that these are not entirely natural objects. He's careful to frame this scientifically. I'm not claiming definitive evidence. I'm arguing that the probability distribution of hypotheses should include technological origin as a non-zero possibility, perhaps even a significant possibility. We should investigate accordingly with appropriate rigor and skepticism, but without a priori dismissal. What would a technological origin even mean? Dr. Loeb proposes several scenarios. Scenario 1. Ancient solar system technology, perhaps billions of years ago. When the solar system was young, something, whether indigenous life or visitors, created objects with technological components. These objects have been orbiting ever since, slowly degrading but retaining some functionality or structure. The Chimera would be archaeological artifacts in space. This explains why they're gravitationally bound to our sun. They've always been here. It explains the mix of natural and unusual materials. They were built from solar system resources using techniques we don't understand. And it explains why they're inactive now. They're broken, exhausted, or shut down after billions of years. Scenario 2. Interstellar probes. These could be probes from another star system, captured by our sun's gravity billions of years ago. Similar to Dr. Gladman's alien Oort cloud hypothesis, but artificial rather than natural. They've been dormant in the outer solar system, possibly activating periodically, or when entering the inner system. This explains the unusual composition, built from materials from another star's planetary system, the apparent guidance, residual functionality, and the family of objects, multiple probes from the same mission or civilization. Scenario 3. Ongoing monitoring system, perhaps most provocatively. These could be actively functioning probes that are currently observing our solar system, particularly Earth. The periodic appearances, the apparent guidance, the heat generation all could be consistent with operational technology. This is the scenario that makes most astronomers deeply uncomfortable, not because it's impossible, but because it feels too much like science fiction and too little like science. Dr. Jackie Faherty at the American Museum of Natural History represents the skeptical mainstream position. She argues, extraordinary claims require extraordinary evidence. While C-2023E1 is indeed extraordinary as a natural object, the evidence for technology is circumstantial and interpretable through natural frameworks. We should continue observing and analyzing, but we should demand much higher evidence standards before invoking artificial origins. She points out that in the history of astronomy, many apparently anomalous objects were eventually explained naturally once we understood them better. Pulsars were briefly considered as possible alien beacons before we recognized them as rotating neutron stars. Fast radio bursts seemed inexplicable until we found natural sources. Tabby stars' bizarre dimming pattern suggested megastructures until we found evidence for circumstellar dust. The pattern, Dr. Faherty notes, is that weird stuff is usually just nature doing something we haven't seen before, not aliens. But Dr. Loeb counters. Science advances by following evidence, not by adhering to what we're comfortable believing. If the evidence points toward technology, we should investigate that possibility with the same rigor we bring to natural explanations. Otherwise, we risk missing something profound because it makes us uncomfortable. This is the fundamental tension. How do we balance appropriate skepticism with genuine open-mindedness? At what point does an accumulation of anomalies justify considering alternative explanations? Dr. Ravi Kumar Kaparapu at NASA Goddard has proposed a quantitative framework for assessing this question. He developed something called the Artifact Assessment Protocol, a mathematical framework for calculating the probability that an observed object is technological versus natural, based on the number and severity of anomalies it exhibits. When he applied this protocol to the Chimera, he got a result that surprised him. Depending on how you weight the various anomalies, the technology hypothesis achieves between 15% and 40% probability. That's not definitive natural explanations still dominate the probability space, but it's high enough that, in Dr. Kaparapu's words, we'd be remiss not to investigate it seriously. His paper proposes a series of observations and analyses that could potentially distinguish between natural and artificial origins. High-resolution imaging to look for surface structures inconsistent with natural formation. Detailed magnetic field mapping to determine if the field sources are organized. Radio observation to detect any electromagnetic emissions. Though, after months of listening, nothing has been detected. Chemical analysis to look for isotope ratios or molecular structures characteristic of industrial processes. Trajectory analysis over longer time baselines to determine if course corrections continue. And ultimately, he argues, we should consider a direct mission a spacecraft to rendezvous with one of these objects and examine it up close. The Parker Solar Probe flyby proved we can get close to these objects with existing spacecraft if trajectories align. But flybys provide limited data. To really understand what the Chimera and its cousins are, we need to go there, match orbits, and study them up close, maybe even touch them, sample them, analyze their materials directly. Several mission concepts have been proposed since the discovery of the Chimera in March 2023. Project Interlocutor, a European Space Agency concept for a small, fast spacecraft that could be launched on short notice to intercept objects of interest. It would use solar electric propulsion to catch up with targets and perform close flybys with high-resolution imaging, spectroscopy, and magnetic field measurements. Cost: approximately €400 million. Timeline: 7 to 8 years from approval to launch. Chimera Rendezvous Mission. A NASA concept for a more ambitious mission that would actually orbit one of the fragments, probably Fragment B, since it's still active and observable. The spacecraft would carry a suite of instruments similar to what was on the Rosetta mission, plus equipment specifically designed to detect technosignatures if they exist. This would include radio receivers, magnetic field mappers, and a lander that could sample the surface. Cost: approximately $1.5 billion. Timeline: 10 to 12 years from approval to arrival. Rapid Response Network. Not a single mission, but a proposal by an international consortium to maintain a network of prepared spacecraft that could be launched quickly when interesting objects are discovered. Think of it like having ambulances ready before someone gets hurt. These spacecraft would be built, tested, and stored, ready for rapid deployment. Cost: approximately $3 billion for a network of 5 spacecraft. Timeline: ongoing capability after initial deployment. Here's the challenge. Space missions take time. By the time we design, fund, build, launch, and fly a mission to one of these objects, years will have passed. Fragment C is moving away from Earth right now. Fragment B is receding toward the outer solar system. Opportunities for efficient trajectories come and go based on orbital mechanics. Dr. Tom Statler, NASA's program scientist for the Solar System Exploration Division, explained the problem. We're in a frustrating situation where we've discovered something potentially revolutionary, but our ability to follow up is limited by the realities of spacecraft development timelines and orbital mechanics. We might have a window of optimal access for only a few years, after which these objects become much harder to reach. But here's the interesting development. Private space companies have expressed interest. In October 2024, a consortium including SpaceX, Blue Origin, and several smaller space ventures approached NASA and ESA with a proposal to fund and conduct a rapid mission to Fragment B using commercial spacecraft and partially private funding. The proposal suggested they could launch within 3 to 4 years if agencies provided scientific instruments and mission planning support. This creates a complicated situation. Scientific missions are typically conducted by space agencies with rigorous oversight, peer review, and public accountability. A private mission would operate differently, potentially faster and more flexibly, but with less scientific community input and potentially proprietary data restrictions. Dr. Lindley Johnson, NASA's Planetary Defense Officer, yes, that's a real title, has been coordinating discussions between agencies and private companies. He notes, there's precedent for public-private partnerships in space science. NASA regularly contracts with private companies for launch services and spacecraft manufacturing. The question is whether we can structure a partnership that maintains scientific integrity while leveraging private sector speed and innovation. As of my knowledge cutoff in late January 2025, negotiations were ongoing. The European Space Agency was leaning toward a pure science mission with traditional structure. NASA was exploring the hybrid public-private approach. Japan's JAXA was considering whether they could repurpose an existing spacecraft or fast-track a new lightweight probe. Meanwhile, there's another approach being seriously discussed: waiting. Fragment A is now dormant and following a well-characterized orbit. Fragment C is similarly inert and trackable. Fragment B is active, but stable. All three will remain accessible for decades. Perhaps instead of rushing a mission, we should take time to design the optimal investigation, learn from ongoing observations, and launch a comprehensive mission in the 2030s when technology is even better. Dr. Carol Cleland, a philosopher of science at the University of Colorado Boulder, has been thinking about the epistemological questions raised by this situation. In a thought-provoking paper, she asks, what level of evidence do we require before we can justifiably claim to have discovered extraterrestrial technology? And what are the consequences of setting that evidentiary bar too high versus too low? If we set it too low, we risk claiming detection when we've actually just found exotic natural phenomena, potentially embarrassing the scientific community and spurring unwarranted public panic or excitement. But if we set it too high, we risk dismissing genuine artifacts as natural because we're unwilling to accept evidence that challenges our worldview. Dr. Cleland argues that the chimera presents a test case for how we approach this question. She advocates for what she calls symmetrical skepticism, being equally skeptical of both natural and artificial explanations, following evidence wherever it leads without predetermined conclusions. The worst outcome, she writes, would be to dismiss the possibility of technology, not because the evidence argues against it, but because we find it conceptually uncomfortable. Science advances by confronting uncomfortable possibilities and testing them rigorously, not by reflexively defending the status quo. Let's think about what it would mean if the chimera and its cousins are truly artificial probes, artifacts, or technology of some kind. The implications cascade in ways that affect almost every aspect of how we understand our place in the universe. First, the immediate implication. We are not alone. If these objects are artificial, they were made by something with technological capability. Whether that civilization still exists, whether they're aware of us, whether they're from our galaxy or beyond, all become urgent questions. Dr. Douglas Vakuk, president of METI International, Messaging Extraterrestrial Intelligence, points out the discovery of extraterrestrial artifacts in our own solar system would be the most profound discovery in human history. It would answer the question, are we alone? Definitively, and would immediately generate 1,000 new questions about who they are, where they came from, and what they want. But let's be clear, finding artifacts doesn't mean we found living aliens. These objects, if artificial, could be billions of years old, remnants of a civilization long extinct. They could be from a species that lived and died before complex life even arose on Earth. We might be finding archaeological evidence, not contemporary technology. This raises the possibility of something called the Great Filter, a concept from the Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, where is everyone? Why don't we see obvious signs of advanced civilizations? One answer is the Great Filter. Something prevents civilizations from becoming spacefaring or long-lasting. Maybe civilizations inevitably destroy themselves. Maybe interstellar colonization is harder than we think. Maybe advanced civilizations lose interest in expansion. If the chimera is ancient technology, it might suggest that the civilization that built it is gone. They got filtered out. And if they got filtered, despite being advanced enough to send probes to other star systems, what does that say about our chances? Dr. Anders Sandberg at the University of Oxford's Future of Humanity Institute has modeled various scenarios. He argues that finding ancient artifacts would actually be encouraging in one way. It proves that intelligent, technological civilizations can arise. We're not unique in that regard. But it's discouraging in another way. If we're finding artifacts rather than active technology, it suggests that civilizations don't last long or don't maintain their technology indefinitely. Of course, there's another possibility. These aren't ancient. They're contemporary. They're still functioning, still observing, still reporting back to whoever or whatever sent them. In that case, we might be under surveillance right now, and whoever's receiving the data knows we exist and might be watching our development with interest. This sounds paranoid, like conspiracy theory territory. But if the chimera is artificial and currently active, it's not paranoia, it's observation. We would need to consider seriously whether our activities, our radio transmissions, our space launches are being monitored and recorded. Dr. Stephen Dick, former NASA chief historian, wrote about this in what he calls the contact scenario. If extraterrestrial technology is present in our solar system, the question of contact becomes not if, but when and how. Do we attempt communication? Do we approach these objects? Do we leave them alone? There are no protocols, no agreed-upon policies. We'd be making decisions with civilizational implications without precedent or guidance. The second major implication: technology in space is detectable, but we haven't been looking properly. For decades, SETI, the search for extraterrestrial intelligence, has focused on radio signals, laser pulses, and other electromagnetic communications. We've been listening for messages. But if artifacts are common, we should be looking at asteroids and comets more carefully. We should be developing methods to distinguish natural from artificial objects. Dr. Beatrice Vellerol at Stockholm University has started exactly this kind of project. She's using machine learning to analyze archival astronomical images, looking for objects that appear, disappear, or change in ways inconsistent with natural phenomena. She calls it VASCO, vanishing and appearing sources during a century of observations. Her preliminary results are fascinating. There are hundreds of transient things that appear in one image and not in others that have no clear explanation. Most are probably photographic defects, satellite glints, or image artifacts. But some percentage might be real objects that we've been dismissing as noise because we weren't conceptually prepared to recognize them as significant. If we start assuming that some small fraction of solar system objects might be artificial, and we develop detection methods accordingly, we might find that they've been here all along, hiding in plain sight among the millions of natural objects. Third implication: planetary protection policies need updating. Right now, planetary protection is about preventing contamination Earth life contaminating Mars, or returning samples from Mars contaminating Earth. But if there's technology in the solar system, we have a different concern. What if we damage or contaminate an artifact of historical or archaeological significance? Dr. Catherine Conley, former NASA Planetary Protection Officer, raises this concern. If Fragment B or Fragment C are artifacts, they're potentially priceless repositories of information about another civilization. Approaching them crudely, touching them without proper precautions, could damage evidence. We need protocols for archaeological preservation in space, not just biological contamination prevention. Imagine if we send a spacecraft to sample Fragment C, and in the process of landing or collecting material, we destroy surface structures that contained encoded information, or we contaminate the object with Earth materials that interfere with later analysis. We'd be the cosmic equivalent of the archaeologists who dynamited their way into Egyptian tombs in the 1800s, destroying context and evidence in their eagerness to extract treasures. Fourth implication: our models of solar system formation might be incomplete. Even if these objects are natural, just really weird natural, they're telling us that the solar system can produce things we never anticipated. Our models of how planets, asteroids, and comets form are based on the objects we've studied so far. But those models might be missing entire categories of objects or processes. Dr. Kevin Walsh at Southwest Research Institute works on solar system formation models. He notes, every time we discover something truly unexpected like interstellar objects passing through, or asteroids that outgas, or now the Chimera, it tells us our models are incomplete. The solar system is more complex, more diverse, more capable of surprises than we've given it credit for. That's scientifically exciting, but it also means we're less certain about things we thought we understood. This has practical implications. If we're planning missions to asteroids for mining or deflection to protect Earth from impacts, we need to understand the full range of objects that exist. If some asteroids or comets have properties we haven't accounted for, unusual compositions, internal structures, magnetic fields, our mission plans might need adjustment. Fifth implication: This affects how we search for life elsewhere. If strange objects like the Chimera exist in our solar system, they probably exist around other stars too. Exoplanet researchers studying distant planetary systems might be missing important features of those systems because they're focusing on planets and ignoring the small bodies, the comets, asteroids, and possibly artifacts that could tell us a lot about those systems' histories and current conditions. Dr. David Kipping at Columbia University has proposed that we should look for exocomets around other stars, comets transiting in front of distant stars, creating detectable dimming patterns. His team has found evidence for exocomets around several stars. But what if some of those are not natural comets? What if some are technological objects? The tools we're developing to study exoplanet spectroscopy, transit photometry, direct imaging could potentially detect large artifacts around other stars if we know what to look for. The Chimera might be teaching us the signatures of extraterrestrial technology, even if it turns out to be natural after all. Let's talk about how this discovery has affected people, because the Chimera isn't just a scientific puzzle. It's become a cultural phenomenon that's revealing something about how humanity deals with profound uncertainty. When news of the Chimera first broke in scientific circles in March 2023, it was a niche story. Astronomers were excited, but the general public barely noticed. The mainstream media ran a few stories with headlines like "Mysterious Comet Baffles Scientists," but it didn't go viral. That changed in May 2023 when the fragmentation occurred and Fragment C appeared to make course corrections. Suddenly, social media exploded. The hashtag Chimera Comet trended on Twitter. YouTube videos with titles like "Alien Probe Confirmed in Solar System" got millions of views. TikTok astronomers and science communicators tried to explain what was actually known versus what was speculation. Dr. Frank Marchus at the SETI Institute noted an interesting pattern. The public response split along predictable lines. Some people immediately assumed it was aliens and got very excited. Others dismissed any unusual claims as conspiracy thinking and insisted it must be natural. Very few people seemed comfortable sitting in the uncertainty, the space of we genuinely don't know yet. This discomfort with uncertainty is psychologically interesting. Humans crave definitive answers. We're pattern-seeking creatures who get anxious when patterns don't resolve into clear meaning. The Chimera is Rorschach test people, see in it what their priors tell them to see. Skeptics see another overhyped astronomical oddity that will inevitably be explained naturally, just like all the others. Believers see the evidence they've been waiting for, that we're not alone. Scientists see a fascinating puzzle that requires more data. And most people oscillate between these positions, depending on which new piece of information they encounter last. There's also been a political dimension. In July 2024, several members of the U.S. Congress held informal discussions about the Chimera in the context of ongoing UAP, Unidentified Anomalous Phenomena, formerly UFO, investigations. Some representatives argued that if there's any possibility the Chimera is artificial, it should be investigated with the same seriousness as terrestrial UAPs. Others argued that scientific anomalies should be left to scientists, not made into political issues. Dr. Nadia Drake, a science journalist and daughter of astronomer Frank Drake, who created the famous Drake equation for estimating civilizations in the galaxy, wrote an insightful piece about this. The Chimera has become a proxy for larger cultural anxieties. People who believe government is hiding evidence of aliens see it as vindication. People who believe science is under attack from irrationality see it as dangerous pseudoscience. But the object itself, whatever it is, doesn't care about our cultural moment. It is what it is, and only careful observation and analysis will reveal its nature. There's also been an interesting response from religious and philosophical communities. Dr. Jennifer Wiseman, an astronomer and director of the American Association for the Advancement of Science's Dialogue on Science, Ethics, and Religion, has been thinking about how discovery of extraterrestrial technology would interact with religious worldviews. She notes, most major religious traditions are theologically flexible enough to incorporate the existence of other intelligent beings. The Bible, Quran, and other texts don't claim humans are the only intelligent creatures God created. That's an assumption we added later. Finding evidence of other technological civilizations would be surprising, but not theologically devastating for most traditions. Others disagree. Some religious thinkers argue that discovery of aliens, especially technologically advanced aliens who existed billions of years ago, would fundamentally challenge human-centric theology. If we're not special, if we're just one among countless intelligences scattered through space and time, what does that mean for doctrines of salvation, chosen people, or divine purpose? These are the kinds of conversations happening in church basements and synagogue study groups, in online forums and philosophy departments. The Chimera, even before we fully understand it, is making people think about big questions. Who are we? Where do we fit in the universe? What is our purpose? Dr. Ted Peters, a theologian at the Pacific Lutheran Theological Seminary, conducted surveys asking people how discovering extraterrestrial intelligence would affect their religious faith. Interestingly, most respondents said it wouldn't fundamentally change their beliefs. They'd simply incorporate the new information into their existing frameworks. But a significant minority, about 25%, said it would cause serious reconsideration of their worldview. The Chimera is also affecting how we think about our future. If these objects are ancient artifacts from a civilization that no longer exists, it's a sobering reminder that technological advancement doesn't guarantee survival. If they're contemporary and we're being observed, it changes how we think about our role in a potentially inhabited universe. Do we need to be on our best behavior because someone's watching? Or should we live as we would anyway, being true to ourselves? These sound like philosophical abstractions, but they have practical implications for how we approach challenges like climate change, nuclear weapons, artificial intelligence, existential risks that could determine whether human civilization lasts long enough to become a spacefaring species. In classrooms around the world, teachers are using the Chimera as a case study in scientific reasoning, critical thinking, and dealing with uncertainty. Students are learning not just about comets and astronomy, but about how science works when confronted with genuinely anomalous data. How do you balance skepticism with open-mindedness? How do you evaluate competing hypotheses? How do you avoid both premature conclusion and paralysis by analysis? These are skills that go beyond astronomy. They're life skills for navigating a complex, uncertain world. Now, I want to talk to you directly. You've been with me for almost 3 hours now, learning about comets, fragments, anomalies, and possibilities. But why should you personally care about the Chimera? How does this affect your life? Let me start with the most obvious. You live in a universe that's stranger than you thought. Whatever the Chimera turns out to be, natural or artificial, it's proven that our solar system still holds profound surprises. You live in a time when we're making discoveries that previous generations could only dream about. Think about that. For all of human history, until very recently, the objects in the night sky were mysteries. Ancient peoples created myths about them. Early astronomers could only observe their positions and motions. Even a century ago, we had barely begun to understand what comets actually were. Now, in your lifetime, we're not just understanding these objects, we're encountering ones that challenge our understanding. We're finding things that might be clues to other civilizations. We're living through a potential contact scenario unfolding in slow motion. This is extraordinary. You are living in an extraordinary time. But there's something deeper here. The Chimera is teaching us humility. For all our technological advancement, for all our scientific knowledge, we still encounter things we can't immediately explain. We're still students of the universe, still learning, still occasionally baffled. This is actually wonderful. It means the universe isn't finished surprising us. It means there's still mystery, still discovery ahead. You haven't been born into a world where everything is known and understood. You've been born into a world where genuine mysteries still exist, where the boundaries of knowledge are still being pushed outward. And you're part of that. Every time you look up at the night sky with curiosity, every time you ask questions about how things work, every time you engage with scientific ideas, you're participating in humanity's ongoing conversation with the cosmos. You're part of the same tradition that includes Galileo looking through his telescope, Caroline Herschel discovering comets, and the team analyzing data from James Webb Space Telescope. Here's another personal angle. The Chimera challenges you to think about what you believe and why you believe it. Do you think we're alone in the universe? Why? Do you think everything has a natural explanation? What would it take to change your mind? These aren't just abstract philosophical questions. They're questions about how you process information, how you evaluate evidence, how you balance skepticism and openness. The Chimera is a test case for your epistemology, your theory of knowledge. If you find yourself immediately certain that the Chimera must be natural, ask yourself, am I following evidence, or am I defending a comfortable position? If you find yourself immediately certain it must be artificial, ask yourself, am I being appropriately skeptical, or am I seeing what I want to see? The truth is, none of us knows yet. The most intellectually honest position is uncertainty combined with curiosity. And that's a valuable mental posture to cultivate being comfortable not knowing while actively seeking understanding. This applies far beyond astronomy. In your life, you encounter ambiguous situations constantly. Relationships where someone's intentions aren't clear. Career decisions where outcomes are uncertain. Political and social issues where good people disagree about facts and values. The skill of sitting in uncertainty while gathering information, of holding multiple hypotheses simultaneously, of proportioning belief to evidence. This is what the Chimera can teach you. Let's also consider what it means if the Chimera is artificial. If it's proven that these objects were made by another civilization, you, reading this or listening to this, will be among the first humans in history to know for certain that we're not alone. You'll be living through the most significant discovery in human history. That's not hyperbole. The discovery of extraterrestrial intelligence would be bigger than the invention of agriculture, bigger than the Industrial Revolution, bigger than the space age. It would be a pivot point in human history, a before and after moment. And you'd be there for it. Your children or grandchildren would ask you, what was it like when we discovered we weren't alone? And you'd be able to tell them. You'd be a first-hand witness to humanity's coming of age, the moment we realized we're one among many. But even if it's natural, even if the Chimera is just a really weird comet, you're still living through something remarkable. You're alive at a time when our technological capability has reached the point where we can study objects in detail that would have been invisible to previous generations. You're alive when artificial intelligence can help analyze astronomical data, when international collaboration makes discoveries possible, when you can watch in real time as scientists puzzle through mysteries. You have access to knowledge that would have made you the most informed person on the planet just a few centuries ago. You can learn about exoplanets, black holes, quantum mechanics, the history of the universe from the Big Bang to now. You live in an age of unprecedented access to understanding. Don't take that for granted. The fact that you've spent these hours with me learning about the Chimera is itself remarkable. You could have spent this time on entertainment or distraction, but you chose to engage with complex ideas, to stretch your mind, to grapple with uncertainty. That choice matters. It means you're the kind of person who values understanding, who seeks knowledge, who wants to comprehend the universe beyond your immediate concerns. That's not universal. Many people don't have that curiosity, or they've had it educated out of them, or they're too overwhelmed by daily survival to indulge it. But you're here, you're engaged, you're thinking. And here's what I want you to take away personally. You matter in this story. Not because you're going to discover the next anomalous comet, though maybe you will amateur astronomers discover things all the time, but because you're part of the collective human consciousness that's encountering this mystery. Your curiosity adds to humanity's collective curiosity. Your questions add to our species' question-asking. Your wonder adds to our shared sense of awe at the universe's complexity and beauty. When we eventually figure out what the Chimera is, whether that's next year or next decade, it will be because thousands of people like you cared enough to pay attention, to learn, to think. Science isn't just done by scientists in labs. It's done by a whole civilization that values discovery, that celebrates curiosity, that makes space for people to ask why and how. And what if you're part of that civilization? You're part of the team. So where do we stand as of my knowledge cutoff in late January 2025? Let me give you a current status update and tell you what's coming next. Fragment A is dormant and traveling outward through the solar system. It's no longer observable with most telescopes due to its distance and lack of activity. Its orbit is well characterized. We know where it is and where it's going. Unless it somehow reactivates, which would be astonishing, it's essentially a closed chapter. We got what data we could, and now it's gone. Fragment B is still active, still exhibiting those periodic brightening events, still generating internal heat. It's currently beyond Mars's orbit and heading outward. The James Webb Space Telescope conducted additional observations in December 2024 that I don't have detailed results for. They were still being analyzed as of my cutoff. But early reports suggested the heat signature remains anomalous and the chemical activity continues. There are plans for more JWST observations in mid-2025 and possibly Hubble observations if scheduling permits. Ground-based telescopes continue to monitor as well, though the object is getting fainter as it recedes. Fragment C remains the most intriguing. The Parker Solar Probe flyby data is still being fully analyzed. There's so much data that it takes months to process completely. The images showing possible geometric features have been scrutinized intensely. Some researchers see clear evidence of linear structures. Others see pareidolia, the tendency to see patterns in random data, like seeing faces in clouds. There's talk of pointing additional space telescopes at Fragment C for higher resolution imaging. The Hubble Space Telescope, while old, still has capable cameras. If we can get a clear, high-resolution image showing definitive structure, something unambiguously artificial, that would resolve the debate. But that's a big if. Space is dark, these objects are small, and even our best telescopes have limits. The original parent object, the Chimera before it split, is presumably gone, having broken into the 3 fragments we've been tracking. But some astronomers have speculated that there might be additional small fragments we haven't detected, pieces that broke off during the fragmentation event and are too small or dim to observe easily. These could be anywhere in the vicinity of the 3 main fragments' orbits. As for the 17 archival objects Dr. Zhang identified, most are currently unobservable. They're either too far away, too faint, or in parts of their orbits where they're behind the sun from Earth's perspective. But several are due to return to the inner solar system over the next 5 to 10 years. When they do, you can bet every major observatory will be watching. In particular, Object C2016R3 will make a relatively close approach to Earth in 2027. If we're lucky, it might reactivate or do something interesting that gives us more data to work with.